Hi everyone. This screencast is going to be a quick discussion about what happens when we have systems of equations in three variables. So the first one I've got here is the equation 2x minus y plus 3z equals 5. I'll just display that one. So unsurprisingly, that is the equation of a plane, a two-dimensional plane in 3D space. Now, you will recall when the equation is written in this form, we can tell the normal vector of this plane, a vector normal to this plane, would be 2i minus 1j plus 3k. That's fine, just a bit of something we learnt from previous lessons. Now, here's a second plane. 2x minus y plus 3z equals negative 2. You'll straight away notice that the coefficients of x, y, and z are the same as in equation 1. The constant term is different. This means that the normal to plane number 2 is the same normal. Now, what does that mean? Well, that means, of course, that the planes are parallel. So I've just turned the second one on. The different constant here means they'll be offset a little bit. There'll be a gap between them, but the planes are definitely parallel. Now, what happens if I try to solve those two systems? There's two equations in three unknowns. I won't get a unique solution by any means, but what happens if I try to solve that? So you can see here what I've done. I've entered an augmented matrix. 2 minus 1, 3, 5, that's equation 1. Then 2 minus 1, 3 minus 2, that's equation 2. So immediately you can see the coefficients are the same. Something's going to be a bit off. When we do reduced row echelon form, this is the result. I'm pretty sure that, yeah, that's the result. Now look at that second row in the table. It's a classic sign, 0, 0, 0, and then a non-zero constant at the end. That can't be right. That literally would translate into the statement 0x plus 0y plus 0z equals 1. In other words, 0 equals 1. Completely untrue. This is a sure sign. If you get a row in if you've done a Gaussian elimination process or reduced row echelon form, you end up with a statement like this where all of the coefficients are 0 and then there's still a non-zero constant. You have inconsistent equations. There is no solution. As you can see here, these planes are parallel. That's that one. Now let's take a look at a different situation. What if I turn on equation 3 here? So equation 3, perfectly good 2D surface, a plane. So the normal would be 1i plus 4j plus 2k. And equation number 4 here, the normal for this one is different. You see 2, 1, negative 1 coefficients are different. So our planes are definitely not parallel. Now, what happens when two planes are not parallel? Well, they intersect, and they intersect in a line. So I'll just highlight the line. Now, I have explained in a previous lesson about how you can solve those two equations to get the equation of the line. So I won't go back through that now, but there is the line of intersection between the two planes. Now, what happens on our matrices if we try to do this one? So I'll just have to enter the new results. So our first equation 3 was 1, 4, 2, negative 1. And equation 4 says 2, 1, negative 1, 4. And when I do the reduced row echelon form this time, take a look at this. No inconsistencies going on here. There will not be a unique solution, of course, because we only have two equations, but there are three unknowns. Now, this is giving me a relationship between y and z equaling, so 1 times y plus 5 over 7 times z must always equal the constant negative 6 over 7. And the first one gives me a relationship between x and z. Now, if you'd like to know how to go from that result there on your matrix into this equation over here, or the vector form of the equation of a straight line, then that's the topic of a previous lesson that you can go and review. So in the nutshell, two planes in 3D space, they will either be inconsistent, where the planes are parallel, or they will intersect in a line. That's enough for this one. Next one will be about what happens when we have three planes in 3D space. Thanks for watching.